We're going to look at homogeneous linear systems of differential equations with constant coefficients. We're not going to jump right into solving. I'm going to use what we're looking at to introduce some concepts here. We have a system dx dt equals 2x plus 2y, dy dt equals 3x plus 3y, which can be represented as the matrix equation x prime equals the 2 by 2 matrix 2, 2, 1, 3 times x. X, the vector on the right, is the column vector xy, and x prime is the column vector dx dt dy dt of derivatives. The solution to the system is x of t equals c1 times the column vector 1, 1 times e to the 4t plus c2 times the column vector 2, negative 1 e to the t. This is a superposition of two solutions. x1 of t is equal to 1, 1 e to the 4t, and x2 of t is equal to 2, negative 1 e to the t. These have the form x of t is equal to ke to the lambda t. Lambda is called an eigenvalue. It's the solution to a particular equation that we're going to look at later. K is what we call an eigenvector. And it's actually the eigenvector associated with an eigenvalue lambda. So that you can see the relationship between an eigenvector and an eigenvalue, and its relationship to a matrix. Here, I'm going to write down an equation. Suppose we write down 2, 2, 1, 3. That's the coefficient matrix for the system of differential equations that I introduced. And we're going to multiply that by 1, 1, the vector I gave for the first solution, x1. Using matrix multiplication, what we see is that we have 2 plus 2 for the top entry, and then 1 plus 3 for the bottom entry, which equals 4, 4. And you'll note that that is 4 times the vector 1, 1. The vector 1, 1 is the vector that we started with, and when we multiplied that by the matrix A, we ended up with a scalar multiple 4 times the vector. Our equation then has the form AK is equal to lambda k. Multiplying the vector k by the matrix A gives the same result as multiplying that vector k by the number lambda. Lambda is an eigenvalue of the matrix A, and k is its associated eigenvector. Part of our work is going to be to find lambda and then to find k, and then construct the solutions that we just looked at and superposition them to write down the general solution to a system of equations. Since our systems have constant coefficients, we're going to suppose that the vector function x equals ke to the lambda t is a solution to the system x prime equals ax. And now we're going to do what we've done a bunch of times in this course. We have a proposed form of solution. We're going to plug it into the differential equation and see what happens. So x is equal to ke to the lambda t. What we need its derivative for the left-hand side of this equation. And so we only need to differentiate the exponential because the k vector is constants. So x prime is equal to k lambda e to the lambda t. And the equation that we have, x prime equals ax, then becomes k lambda e to the lambda t is equal to a k e to the lambda t. Since e to the lambda t is never equal to 0, we can divide that out. We get that k lambda is equal to a k, that eigenvalue eigenvector equation. And then by subtracting, we get that a times k minus k times lambda is equal to 0. And that's the 0 vector. Now, suppose I want to factor out the vector k. I then end up with a bit of an issue here, because what I would be left with would be a minus lambda times k, but this is a problem because a is a matrix and lambda is a number, and we can't subtract a matrix from a number. They aren't the same kind of thing. So to turn lambda into a matrix without affecting its lambda-ness, we're going to multiply by I. In the same way that if you had 3x plus 3 and you factored out a 3, you'd write down x plus 1. That 1 is the result of factoring 3 out of 3, right? So the matrix version of that is that we get I. And the resulting equation is the quantity a minus lambda I times k is equal to the 0 vector. Well, now, folks, this is a system. It's a system of the form ax equals 0. Something I didn't mention before when I told you what an eigenvalue and an eigenvector was is that the vector k, by a definition, cannot be the 0 vector. Back to the system, the quantity of a minus lambda I times k equals 0, we're looking then for non-trivial solutions. In other words, solutions for which k is not equal to 0. A linear algebra result that I quoted in the previous video is that then the determinant of the coefficient matrix, or in this case, a minus lambda I, will then equal 0. This results in an equation. We know what a is, and we know what I is. We would be trying to find lambda through this equation, and that's what I meant up here when I said that lambda is the solution to an equation. Once we have the solution to the equation, then we kind of work backwards a little bit. A minus lambda I times k is equal to 0 gives us a system, and k then becomes an unknown vector that we're looking for. This equation, determinant of a minus lambda I equals 0, is called the characteristic equation. It's actually the characteristic equation for the matrix A, but for our purposes, we're going to call it the characteristic equation for the system. The solution to the characteristic equation gives us lambda, and then once we have lambda, we then use it to find k.